Alright, so begins lecture 22 on congruence of surfaces. This is section 6.9 in O'Neill. If you hear some strange music in the background, that's just my son, Matthew. He's, well, he hasn't had many lessons yet, let's just say. Anyway, so two surfaces, M and M bar, are congruent. What that means is there's some isometry of 3 dimensions, right? Which, remember, means that it's a rigid motion, right? It's a rotation followed by translation, and or vice versa. And they're said to be congruent if M bar is the image of M under this Euclidean isometry. So some simple examples. You could take, for example, paraboloid. Oh, actually, what is this? This is like a parabolic trough, really, right? So it's a trough, z equals x squared, and then you can see that that's isometric to z equals y squared plus 1, because you just take the x squared, basically rotate the thing, and then just shift up 1 unit, and it's a rigid motion that takes you from one to the other. Pick any pair of planes you like in R3. Of course, there's some rigid motion which takes you from one plane to another. Planes are congruent, right? So really this goes back to, notion of congruence really is the notion of two surfaces having the same shape, right? And in some sense that's a simpler question than do two surfaces share the same intrinsic geometry. It's a more subtle question. This is, I think, less subtle and more intuitive, more familiar to our ordinary ideas about shape and so forth. But there's the saddle surface. If you rotate that thing 45 degrees, you get this animal. So congruent surfaces have the same shape. So perhaps the following is not surprising. If f is a Euclidean isometry, right, with f of m equal to m bar, then if you take the isometry and you restrict it to the surface M, then that gives you an isometry of surfaces. Furthermore, the push forward of the shape operator is the shape operator of the push forward in this way. Alright, so the push forward and the shape operators sort of commute in this sense. So the proof is given on page 315 to 316 of O'Neill. Essentially follows from some simple facts about restrictions of smooth maps and push forwards of velocities being velocities, and some particulars about how we define the shape operator. It's interesting, it's great, but I'm going to move on, so you can read that proof there. And then the other theorem he has is this: if M and M bar are oriented surfaces in R3, and F from M to M bar is an isometry that preserves orientation of and shape operators. In other words, the push forward and the shape operator commute in the natural way. Oh, now he's driving a train. Then M and M bar are congruent. Moreover, if you take the there exists an a Euclidean isometry. In other words, a rigid motion from R3 to R3, such that you can restrict the rigid motion to the surface, and then that restriction you can identify with the given isometry, which satisfies this shape-preserving condition. Okay, so, and again, the theorem can be found in O'Neill. It's on pages 317 to, oh my goodness, he's attacking me, 317 to 318. Somewhat technical, but it ultimately rests on theorem 5.7, which is analogous to something we proved, but we didn't actually prove theorem 5.7 in chapter 3. It's at the very end of chapter 3. But anyway, I think it's important for you to read the theorem and everything, but I'm not going to spend time on it here. I would point out that the techniques and methods of this theorem are really not much different than the ones I've shown you, so I don't feel obligated to go through it. I think it's more important to understand the result here. And also, probably more important than that, is to understand sort of intuitively, morally, some people might say, the connection between these things. So M being isometric to M bar is sort of like alpha and beta both being unit speed and defined on the same interval. This is probably most clearly, the connection between these two boxes is most clearly revealed in that lemma we had, which said that you can see M and M bar as isometric if basically you could say f of x was equal to y, So in some sense, you know, that's a sort of a kind of a reparameterization or something. I don't know. It's, you can start to see that there, I think. But anyway, this is the what would be analogous. You know, both unit speed defined on the same interval, two surfaces being isometric. And then on the other hand, in terms of extrinsic geometry, there really isn't much intrinsic geometry to a curve, right? Except that you have arc length, and you have arc length. Okay. On the other hand, extrinsically, there's interesting stuff going on for a curve. So you can have curvature and torsion. If those match for two curves, then we know that those two curves were congruent in the sense of high school geometry, which is what I've defined here for surfaces. And likewise here, the previous theorem basically says the same, as that if M and M bar have the same shape operators, then they're congruent. Which just goes to show you that, you know, this term we gave the shape operator was just. It was justified. It does in fact square well against our usual terminology of things having the same shape. And what I think what most folks mean when they say that sort of thing, things have the same shape, means that they're congruent in the sense of high school geometry, which was what I've defined carefully at the start of this lecture. Anyway, that's all I've got for here. Sorry it's so short, but we will move on. Thanks.